Homework 7 is due on Thursday, and we're going to go over one more example today that will address that second book problem. We'll also have the midterm exam on Thursday. As a reminder, bring that equation packet, the FE reference manual equation packet I gave you, and you can also have one page, front side only, with anything you'd like to put on there, including procedure, equations, definitions, and so on. At the end of class today, we'll talk more about some review stuff for the exam. The maps that you're going to generate for the Huntington Sanitary Board project, Stage 3, those should be uploaded before noon on the 31st of October. And there's a spot in MU Online where you can do that. It's live now. So any questions on these announcements? We'll get into the details of the exam a little bit later. All right. Well, we're going to continue talking about evapotranspiration today and then get into a little bit about the concepts of interception. Last time, though, where we left off was this evaporation example we didn't quite get to. It was trying to relate pan evaporation to crop evaporation. So remember that the way that the pan works is it's a surrogate for the amount of evaporation that occurs in the crop, and then you sort of tie together the performance of the pan to the performance of the crop with a series of tables that takes into account where the pan is located adjacent to the crop and the wind speed that there is. And in this example, we have a wind speed of 2.7 meters per second. We're going to use that to find out which pan coefficient we should use. And so we'll remind ourselves the wind speed is 2.7 meters per second. And the relative humidity is 65% in this one. And then the evaporation pan is surrounded by 100 meters of dry fallow on all sides. And the reason why that's relevant is if we go back to the table of pan coefficients, surrounded by dry fallow, 100 meters in all sides. And so dry fallow means we're going to be using this column. The wind speeds of 2.7 meters per second puts us in the moderate range, and the upwind fetch is 100 meters, and the relative humidity that we're given of 65% puts us in this column. And so it tells us that the K value that we're going to use, the pan coefficient, is 0.60. So the K sub P, the pan coefficient, is 0.60. And what that was based on is the upwind fetch of 100 meters. It was dry fallow. Dry fallow being that the crop isn't actually being grown at the moment. A green crop is one thing. It's when the crop is actively growing. Dry fallow is maybe what you'd see in the late fall when the corn has stopped growing and it's sort of yellow and brown and all dried up. The relative humidity put us in the medium range. All right, and so the K sub P of 0.60. In the problem statement, it says that we have pan evaporation of 4.2 millimeters per day. And so E sub P, which is the pan evaporation, is 4.2 millimeters per day. What we're interested to know is what's the monthly reference evapotranspiration for short irrigated grass turf. All right, so the monthly evaporation here, the evapotranspiration, and the reason why it's saying evapotranspiration for short irrigated grass turf is that they use that as a reference crop. They compare different crops to each other, and they'll compare the evapotranspiration of corn to evapotranspiration of this reference crop of short irrigated grass turf, and that's part of what's built into the pan coefficient K sub p, is not only the relationship between the crop and the pan, but also the crop and whatever reference crop is being used. So K sub p, E sub p, and our K sub p here is 0.60, and the reference evaporation for the pan, 4.2 millimeters per day, and then we multiply that by 30 days per month. And that gives us that there will be 75.6 millimeters of evapotranspiration per month. And that's for the short irrigated grass turf. Now, this next question is a conceptual question as much as it is actual problem solving. How much irrigation should farmers provide? We've just calculated how much evapotranspiration there's going to be. And so how would you determine the amount of irrigation that needs to be provided? Okay, very good. Yeah, you'd need to look at the difference between the rainfall and the water demands for the crop, because besides this is how much the crop is evapotranspirating, the crop may be growing during a period of reference. And so at one period of time where the plant mass is relatively small, the evapotranspiration would be lower than if the crop is grown a lot towards the end of the month. And so not only is it a function of the difference between precipitation and evapotranspiration, but also wanting to provide excess to account for the growth of the crop, and of course the soil conditions can change over time as well. There could be erosion of the soil, or the soil moisture may increase or decrease because of consecutive really hot days, to where it changes the infiltration rate. So there are a lot of variables, but that gives you a rough idea of how pans are used to keep track of irrigation needs for crops that are being grown. There are certain parts of the U.S. where the crops really aren't irrigated at all. I think probably in Iowa and further towards the east, they don't really irrigate as much. But if you get into Nebraska and Kansas, then you'll see large swaths of agricultural regions that have these really, really big pipelines and sprinkler systems where they're irrigating the crops. It's kind of interesting when you're driving cross country to see all that. The mass transfer approach that's at the heart of question 7.2 from the book is just sort of another way of looking at the aerodynamic method. And really, as much as everything else, the value of having this problem in your homework set is just to see how some of the equations look familiar, and in fact we've used them before. Excuse me. But the different notation systems that are used from one text to another, it's just enough to throw you off and make you have to proceed very carefully through the calculations. The mass transfer approach basically is saying that there's going to be as much evapotranspiration as the moisture is able to be moved away from the surface. And one of the key things here, one of the key assumptions the book tells you to make, is that the saturation vapor pressure at the surface is equal to the vapor pressure at the surface. And what that essentially is meaning is that it's assuming 100% saturation in the air immediately above the water surface. And another thing that your book sort of falls down on is this equation where you can calculate the saturation vapor pressure at the surface. This same form of the equation can be used to find the saturation vapor pressure for the air. And in fact, this equation isn't shown explicitly in the text, but the truth is that you can substitute the temperature of the surface and find the saturation vapor pressure at the surface, but you can also use the temperature at the air and find the saturation vapor pressure in the air. So just to illustrate how the mass transfer approach is used, we're going to look at a quick example, and in fact this is the example taken from the text. So there's a certain lake that has an area that's given, and the purpose for providing the area is it defines this K sub E. And the K sub E is a coefficient that tells you how efficient vertical transport is. That is how well the air is able to move vertically. And the wind that's defined in this formula here, V sub A, the velocity of the air, that would be a sideways movement of the air. But what they found empirically is that as the lake area increases, you'll notice the factor is that a larger lake would give you a lower transfer efficiency. And why do you suppose that is? That we're calling this parameter K sub E the coefficient of vertical transport efficiency. But if you've got a large lake, you're going to have a lower coefficient of vertical transport efficiency. So just think about, if we do a little drawing, here's a small lake, and the wind is going across it, and we're trying to characterize how much evaporation there is off of this lake. And what this empirical relationship says is that if you have a small lake, you'll have more efficient transfer of moisture vertically than if you've got a large lake. How does that square with what we know conceptually about evapotranspiration and evaporation from a free surface of water? Any idea why the small lake is more efficient at moving moisture around than the large lake is less efficient? Yeah?
Is it because small lakes usually shallower, so you have more surface area for volume?
You're headed in the right track, but the volume of the lake actually doesn't matter. Since it's only the surface area that the evapotranspiration is occurring at, the lake can be shallow or it can be very deep and not really have much of an impact on evapotranspiration. The exception to that is that, of course, a lake is going to have a temperature profile, and a shallow lake will heat up and cool off more quickly than a deep lake. And of course, one of the driving factors in evapotranspiration is the difference in the air temperature and the water temperature. And so a large lake that stays warm longer is going to have more evapotranspiration than a shallow lake that cools off more quickly. And so that's really the only case where the lake volume would have an effect. But it is partly related to the surface area. And if you think about it, the water molecule that's trying to escape, let's say if the wind is going from left to right, by the time the wind makes it all the way over to this part, it's fully saturated with moisture. And so a large lake is going to have less capacity to absorb the liquid that's in the lake on a per area basis, because this small lake, you've got dry air passing over the lake, and it's still relatively dry by the time it gets out. And the driving force between evapotranspiration, when we consider the aerodynamic, or as it's called here, the mass transfer approach, is one of the driving forces you look at is the difference between the saturation at the surface and the saturation in the air. The evapotranspiration rate is how much moisture essentially could be in the air versus how much is there. And so still, too many L's, still pretty dry. So in this case, if you've got a large lake, you have dry air coming out, and maybe by the time it gets halfway through, the air is fully saturated. And so there isn't going to be any further evapotranspiration or a very minimal driving force in evapotranspiration once the air packets that are moving sideways get over the middle of this very large lake. And so the empirical expression here is trying to take into account the relationship between lake size and the actual evapotranspiration that occurs. Now, of course, there's a weakness in that, because if we are looking down from above on a lake, you could have a circular lake, or maybe you've got a lake that's very long and narrow. And so there could be times when the wind is going this way over the lake, and it would be evapotranspirating just fine because it's so narrow. By the time the dry air gets to this edge, it's still fairly dry. But if the wind was going this way, then maybe that empirical expression, if anything, would be understating how inefficient the lake is at vertical movement of the moisture, because it's got such a long fetch of water that the wind is traveling over, that the evapotranspiration would be very low. One of the things on the exam that I'll just throw out right now is that about half of it is going to be conceptual questions, and that should come as no surprise. You know from the quizzes that we've taken that there's just a lot of conceptual material in the course. The exam will be about half problem solving, half concept questions, and so being able to explain relationships and explain the difference between different concepts is going to be an important part of the exam. And so when it comes to evapotranspiration, I'm going to hope that you can plug numbers into these empirical equations and find how much evapotranspiration happens during a certain period, but at the same time I hope that you'll be able to explain what are the driving forces of evapotranspiration. All right, so we're going to work this example here. We've got a lake with a certain area, and we're going to go through the process of calculating the evapotranspiration for a certain day. Uh-huh.
So when it was blowing across the lake at the skinny portion,
Yeah.
and the air wasn't being fully saturated.
Right.
But when it was blowing the long way it was, so long way be taking more moisture off of the water because it's fully saturated.
No, because evapotranspiration rate decreases as the air gets more saturated. And so let me go back to that drawing because it's a good question. So if we're going this way, what drives evaporation is the difference between moisture content and maximum So what drives evaporation is how far apart the evaporation, how far apart the moisture content is and could possibly be. So if the air could hold, I'm trying to think of what's the best way to describe it. You know, if the partial pressure of moisture in the air could possibly be 4 kilopascals, and there's only 1 kilopascal of moisture in the air, then the difference of 3 is the driving force. But as the air becomes more saturated with moisture, then the driving force is smaller and the evaporation rate decreases. And so what's good, we're going to have lots of evaporation in this case, evaporation high, simply because it's not the air is not saturated. So you've got dry air that's coming over the water, and that dry air there's a big difference between how much moisture is there and how much could be there. And because of that large difference, that's the driving force that how much moisture is taking out of the water. And so here we could say in the water, what's above the water here? Above it is very dry air. Whereas in the case of the dry air is coming this way now, okay? So above it initially, here, what's above it is dry air. But by the time we get to here, you know, the wind is still going this way. What's above it now is wet air because there's already been a lot of evapotranspiration. So what's above it is air that's saturated with moisture, and so it can't really hold any more moisture. And so the whole rest of the lake, there isn't going to be evapotranspiration because what was above it was that moist air. Does that address your question? All right. So it's a little bit counterintuitive because you'd think, like you said, that if the air is saturated, that must mean that there was a lot of evaporation. And that's true, but I guess the way to think about it, if I can draw an analogy, and that's always risky because the analogy sometimes breaks down, but let's say that you had 100 pounds of wheat. And how much wheat could you eat if you sat down and you tried to eat it all in one meal? This is, you're trying to eat it all in one long stretch. Whereas this is if you were breaking that wheat up into 10 days. How much of it could you eat? You're saturated. When you sit down, you can eat a little bit, but then you're saturated. You can't eat anymore. So the dry air is eating moisture from the lake, but it's saturated, and then it can't use up any more of the moisture that potentially could be transferred from the water to the air. But here, the dry air isn't saturated by the time it gets to the other side.
Is that maybe because there's more wind going across the lake, there's more wind going across the
Yeah, you could look at it as what's the cross-sectional area of the wind relative to the total area of the lake, yeah. Or it could be the amount of time that a certain packet of air is above the lake. Here, if you ignore turbulence, sideways movement and vortices and eddies and things, if you just assume that it's moving as a mass, excuse me, the air isn't spending much time over the water. But they all are a reflection of the same thing, that what drives evaporation is the difference between how much moisture could be there in the air and how much is. All right, so we were just in the middle of this example where we've got the lake area defined so that we can find the vertical transfer efficiency. And then we're going to try and estimate from the temperatures, estimate the saturation vapor pressure of both at the surface and in the air. All right, so first of all, the K sub E we have 1.51 times 10 to the minus fifth meters per km kPa. All right, we'll use that later. That is from equation 719 in the text. Equation 7.4 in the text says that we can find the saturation vapor pressure at the surface as a function of the temperature. Okay, 17.3 times 26.9 degrees Celsius, 26.9 degrees Celsius plus 237.3. Okay, so the saturation vapor pressure at the surface is 3.556 kPa. And what we know from equation 7.3 is that That's the vapor pressure at the surface. We're assuming saturation. So that is where we've invoked equation 7.3, which says E of S is equal to E star of S. The difference between the star and the not star, E sub S is what is the actual vapor pressure. E star of S means the saturation vapor pressure. And what equation 7.3 says is assume that it's saturated at the surface. Also derived from 7.4, but not explicitly stated, is that you can find the E star A, so that is the saturation vapor pressure in the air, by knowing the air temperature. And we'll put in the 27.2 degrees Celsius there. That is 3.62 kPa. Equation 7.5 relates the relative humidity, the saturation vapor pressure in the air, and the actual vapor pressure in the air. So E sub A tells us how much moisture actually is in the air in terms of its partial pressure, and it's a function of the relative humidity in the air and the saturation vapor pressure in the air. In the problem statement it says it's 69% humidity, so we use 0.69 there, times the 3.620 kPa. That gives 2.50 kPa. And again, that is the vapor pressure of water in the air. So what I've said before is that what drives evaporation is the difference between the vapor pressure in the air and the vapor pressure at the surface. So the difference between how much moisture there could be and how much moisture there is. We'll find the velocity of air, 5.81 meters per second, and we multiply that by 86,400 seconds per day and 1,000 meters per kilometer. Since our constant here was in terms of kilometers, the K sub E constant, its length is in kilometers, so that's why we need to know that the velocity of the air is 502 kilometers per day. So the evaporation rate is K sub E times VA times E sub S minus E sub A. And that is the 1.51 times 10 to the minus fifth meters. You may have noticed that the text, when they're writing the units, they will do the units like this. It's kind of interesting. I might actually start doing the units like that too. It saves you the trouble of having, it's always a little confusing when you write the units like this. Does it mean that the kPa is in the numerator, or do you have to put the parentheses in there to emphasize the fact? But the text has the units where it's just doing to the -1 if it's down in the denominator, or not the -1 if it's not. Have to think about whether I want to make the switch to that permanently. 502 km per day. And then the difference in the vapor pressures. That says that the evaporation rate is 8.00 times 10 to the minus 3 meters per day. That is 8.0 millimeters per day. The homework problem extends this process by giving you the measurement of conditions at every hour of the day. So instead of extrapolating the temperature at 1 hour over the entire 24-hour period, in the book what they do is they give you the surface temperature and the air temperature, the wind speed, and so on for every hour of the day. The homework problem refers to the fact that they've given you a CD at the back of the book. Is anybody bothered with that, or did you just type it in directly? You used the CD? So it worked? The data's there? Okay.
I actually typed it in first, and then it was in a Word format.
So it saved you a little bit of time a second time around. All right. Any questions about this process? Well, let me ask you a question then. So what's the weakness of this model? What's the weakness of estimating evapotranspiration according to this approach? Okay. So there are spatial assumptions, right? There's spatial effects. That's true. Unlimited energy. That's another really big one. Is that remember that the aerodynamic method, and this method too, hasn't taken into account any sort of solar radiation. You'll notice that nowhere in the problem statement did it say how many watts per square meter the solar radiation was, or what should we use for the albedo of the surface, which of course characterizes the reflectivity of it, and how much of the radiation is scattered off into space versus actually absorbed by the water. So when we did the example last time in class and applied the Priestley-Taylor simplification, you remember that the Priestley-Taylor simplification that we used said just assume the evapotranspiration by multiplying the energy method by 1.3. And it ignored the aerodynamic approach completely. And so it seems that most of this is more of a theoretical approach, and most of the applied approaches, like the procedures that are used to actually come up with the actual evapotranspiration rather than the potential evapotranspiration, do include measurements of the solar radiation. That seems to be a very important thing that shouldn't be neglected. So anytime you use a method like this, you need to keep in mind what are the assumptions and what isn't being taken into account that maybe should be. And that'll sometimes explain why the actual evaporation that you see out in the field is very different from what your model predicts. It's just going to be based on what your model accounts for and what it doesn't. The other thing we're going to talk about today is abstractions. And that's a very abstract concept, if you'll forgive the pun. Yeah. Abstractions are, that's awful. I just couldn't resist. Abstractions are anything that gets in the way between precipitation and runoff. And you could potentially include infiltration in that, but most of the things we're going to talk about today, it is not infiltration. It is, you've got rainfall that leads to runoff, and what's in between. You've got a certain amount of precipitation that's falling into a control volume. If we draw a little diagram here to represent a model watershed, here's our control volume, and here's the surface. You've got precipitation coming in. We'll call this rainfall. And there's going to be runoff from that. And there's going to be infiltration. But there's other things as well that will account for the runoff that you see or that you don't see. In class last week, I told you about the project I was doing in the Greenbrier watershed for the DEP. And the model that I put up accounted for evaporation, and I guess I should put that on. We've just been talking about evapotranspiration. Evapotranspiration is accounted for, and there's going to be rainfall and infiltration, runoff, but sometimes there are other things inside of the control volume that have to be accounted for before you can really predict the runoff. And one of them is just as simple as puddles. That figure there is illustrating a puddle. And so an abstraction, the definition of an abstraction is the process or the physical impediments to water being delayed before it enters a discharge system. The water that is intercepted in a puddle eventually is going to evaporate, or the water that's in a large pool eventually may make its way into the runoff, but first it's going to infiltrate slowly, or maybe it'll be stored on the surface of concrete or pavement before it infiltrates, or basically it's just delaying, and routing effects have to be considered to account for the delay. It can also reduce the quantity of discharge that's seen at a certain time. And the reason why abstractions are important is because when we're sizing, for example, a combined sewer, the time of concentration and the amount of flow at any particular time is going to dictate the size of the pipe that's needed. And so if we don't account for these important things that slow down the flow, then we're going to be unnecessarily oversizing the collection network. The peak storm intensity is delayed by abstractions, and accounting for abstractions can be a really important part of getting an effective model. It can also factor the size of a detention pond, and depending on the nature of the abstraction, if it's vegetation that's causing abstraction, it may reduce the need for what sort of treatment is required in order to settle out heavy grits or sand that may clog a pipe network. If water is flowing over grasses, then typically the velocity over the grass is going to be so low that any grit and sediment would settle into the grass and wouldn't make its way into the pipe. And so that would maybe change how quickly the pipe cleaning is scheduled for a certain collection network. So there's a lot of implications that tie into abstractions, and interception is one of the important abstractions. And interception essentially is just plants that temporarily delay the movement of water through the watershed. And you can see here this image is of a raindrop that's just being cupped by a plant, and how much water is intercepted by a plant is going to depend partly on the surface area of the plant that's horizontal. And if this leaf was vertically oriented, it probably wouldn't have the capacity to hold as much water. And so for that reason, a pine tree with its very thin needles isn't going to have as much interception as maybe an oak tree with its broad leaves and a very large surface area of leaf. And so there are tables that characterize different species of plants and how much interception they can actually be counted on to provide. And those tables vary seasonally, because an oak tree in the wintertime isn't going to provide as much interception capacity as an oak tree during the summer. So here's just such a table. There's actually an even more complete one in your book, and what it's showing is that over the year there are certain things that they just have an annual average for the interception. Some of the species will vary between summer or winter. You can see here that in the summertime certain hardwoods would have 30% interception. During the wintertime, 21% interception. So this is one way to understand how plants can delay the movement of water. a certain percentage of the flow is going to be kept by the plant. It can't make its way down to the surface, and then it's going to reduce infiltration and runoff. But how much interception is going to also depend on the storm itself, because if a storm lasts for 7 continuous days, then probably a plant isn't going to have the same capacity to temporarily detain water than it is at the beginning of that 7-day storm. And once the plant becomes fully saturated, then it's not going to delay any longer. And so it's a little bit like infiltration. Remember, in infiltration there was a declining potential rate of infiltration, and we graphed several times that characteristic curve of declining potential infiltration rate. And the reason for it, as time went on, infiltration decreased because the soil voids become saturated. There isn't as much infiltration when all of the empty spots are full. And the same thing is going to be true of plants, that a lawn will have a very effective way of delaying the movement of water when it's completely dry, but after it's been raining and there's a lot of antecedent moisture, then the lawn isn't so effective as an abstraction anymore. So the storm itself can vary the percentage of interception, and so can the local climate. Areas that have extreme humidity conditions, like very dry conditions or very wet, or when there's extremes in evaporation, then these typical values may not quite hold up. And so does the density of the vegetation. If you have a stand of trees that are very tightly packed together, then there's going to be more interception than just a single tree where the branches aren't sort of intertangled like they are in a very dense pack of trees. The age, size, health of the vegetation, and so on. This is one method that's been proposed for trying to estimate the amount of interception. I here is referring to the interception amount, not infiltration. But there is a table here that we're going to use for calculating interception, and from it we can find out the vegetative storage, and it is a depth of water in millimeters that each tree can account for. You can see that this equation takes into account the amount of rainfall, so that it has a declining amount of storage as the rainfall gets bigger and bigger. And that takes into account the same kind of trend that's pictured here. This was a trend that we pictured for soil, and the same thing is true, that there's a declining amount of infiltration. As the storm gets bigger and bigger, a smaller fraction of it is going to be intercepted. This model takes into account any evaporation rate that may occur during the storm, as well as the storm duration. So just to put it into practice, if we were going to say that there is a storm that's 1.5 hours long, 3.8 centimeters of precipitation, and we know that the evaporation rate during the storm is 0.3 millimeters per hour, then why don't you try and calculate for the spruce trees and a leaf area index of 6.5. And what that leaf area index means is, if you're looking down on the tree from above, basically how many layers of vegetation there are in the top view. So, think about a tree. If you are looking down from above on that tree, 6.5 would mean that on average there's 6.5 layers of vegetation. So there would be a leaf beneath it, another leaf, 6.5 on average for the area of the tree. So go ahead and calculate that interception quantity. Abstractions are things that temporarily intercept the flow. It's not a permanent infiltration to the soil. And in this example, what we're trying to find out is of the 3.8 centimeters of precipitation, how much of it is going to be available for runoff and infiltration? In other words, how much of that 38 millimeters of rainfall isn't intercepted by the spruce tree vegetation? And so putting it into the formula for interception, we can calculate that as 9.89 millimeters of interception during this storm. And this is taking into account the evaporation that occurs right off of the leaves themselves. The term K times E times T, that's taking into account the leaf area index of 6.5 for the vegetation and the evaporation amount off of that leaf area. So in total there's 28.11 millimeters of the original 38 millimeters. 28.11 of that precipitation is available for runoff and infiltration. And so there's a term called rainfall excess that we'll get to next week. And I'll bring it up now because it's a little bit confusing sometimes, rainfall versus rainfall excess. And rainfall is obviously just that quantity of whatever falls from the sky. And rainfall excess is rainfall minus abstractions like infiltration and minus interception. And so let me write this down on the board just to be clear about it. Rainfall excess is rainfall minus abstractions minus interception minus infiltration, where interception is one of the abstractions we're talking about. Interception, maybe we're talking about puddles, and so on. Rainfall excess is what we use when we are calculating hydrographs to find the flow coming from a watershed. We're going to get into that in detail next week. Any questions about the interception example? Why do you think that spruce trees have more storage than pine trees? What's that? Okay, yeah, it probably has a greater density of needles. Spruce trees and pine trees are both evergreen. But it's, I suppose, a function of needle density. Depression storage. Water can just sometimes accumulate in surface depressions and puddles, and you can see from the photo here that if this little depression is inside of a watershed, it's going to have to be completely full before anything makes its way to the outlet that has fallen into this depression. And it's not just this pond area that we see here, but anything that feeds into it is also sort of taken out of the equation. And so it looks like there's a bit of a road here. If there is a break line from that road and the water is making its way towards this depression, rather than over the surface, this is going to be, anything upstream of this depression is going to be taken out of the contributing area temporarily until the depression is full. And even after the depression is full, then everything that's inside of the pond is still stuck. Once this depression is full, then the rest of the contributing area is back in the equation. It's going to be contributing to the outflow, but the water volume inside of the pond is going to, inside of the depression is still going to be stuck, and it won't go directly towards the outlet, but it'll just infiltrate into the ground or evaporate. This image is just showing a very flat surface that's paved Runways, of course, are very evenly graded because it's important for airplanes to have a smooth surface when they're going so quickly. And because they're so flat, airport runways are one of the surfaces that are studied very carefully to try and prevent puddles from getting too deep. They put in just a very slight grade to the side of the runway because I'm sure you've heard about hydroplaning before and the risks that that can eliminate the traction in your car. So think about an airplane trying to land and hydroplaning and skidding all about the runway. The possibilities for humor are endless, but so are the possibilities for study. The surface can be considered a storage source, and pavements can be classified in terms of their depression storage. A steep pavement can retain 0.5 millimeters of precipitation, and so the first half millimeter of rainfall is going to be absorbed by the pavement. Even though the pavement we know is impermeable, it's not like the pavement itself is allowing water to go through it. It's just that there has to be a wetting of the surface before the flow begins to move off of it. And this finally is a numerical quantification. We've been talking about surface wetting as one of the things that, for example, changes the C values in the rational method. You'll remember that very early in the semester when we had a table of C values for the rational method, that for a concrete surface, the 2-year storm we said was 0.75, the C value. A 5-year storm is 0.8. A 10-year storm is 0.83. So this relatively increasing C value for a larger and larger storm is basically taking into account the depressions, the surface depression storage being satisfied. And what this is saying roughly is that it thinks about 25% of the 2-year storm has to be going towards satisfying abstractions before there will be runoff. But when you get to the 100-year storm, only 3% of the 100-year storm will be used to satisfy the abstractions before there is runoff. And that's a very general thing, but at least they're in some way addressing the concept of depression storage. You can see that slope is an important thing. A flat slope will retain more water than a steep slope. 3.5 millimeters is a fair amount. That's a lot of water to be on a runway. I think one of the ways that they deal with that is they put very small grooves in pavement. It's not like a very polished surface on a runway, but if you look at it, there are grooves so that they're sort of trying to channelize the flow so that the water can get into these little seams and cracks and flow off to the side, trying to, even though it has to be flat in general, they're trying to channelize the flow as much as possible in the runway. Lawns are going to have a much higher depression storage than a paved surface, and flat roofs may retain quite a bit depending on what is on the roof. Some roofs are stone roofs, and stone roof can have really a lot of storage because it's a granular media where the entire surface of the rock is getting, it's like some roofs are stone in the sense that it's like gravel up on top of the roof to keep the asphalt paper in place. And if all that gravel has to get wet before there's runoff from the roof, then there's a lot of storage there. So you can also already see how slope is being accounted for. Specific surface area is why flat roofs can have such a wide range in depression storage, is that when the flat roof has some sort of a granular media on top, then it has a very high surface area relative to its plan view area. Some of these materials have an affinity for water, and it may vary depending on antecedent moisture condition, how many storms there were in the previous few days leading up to a storm in question. There may be a surface that you'd expect would hold a lot of water. You may be expecting a forest litter to have a very high depression storage, but if it's rained for several consecutive days before an event that you're analyzing, it may be that that storage has already been fully saturated, and maybe it won't account for anything in the next storm. All right, right here stops where the material you're responsible for the exam on Thursday. Right there. That's the break point. This is just a review. So you're still, even though I said that you don't have to know any of this stuff past now, even though I'm talking about this, really these are things that I've introduced already. So it doesn't mean that you're exempted from knowing these things since I'm talking about them now. This is the list of what we've covered this semester so far. And we started the semester by talking about the Huntington Sanitary Board project. And that's been, I think, an important reference point as we're talking about some of the concepts in the course. I've been glad that we've got the HSB project as a context, a point of view. Hopefully you've had a chance to go out there when it's been wet. If not, look for a rainy day and go out there. I think it'll really be instructive to you and help you know where the break lines are for delineating areas, help you know which manholes are taking water and which ones aren't. I mean, you can see if a manhole is, if one of the inlets is clogged and water isn't going in there, there's going to be a dead giveaway if you go out there on a rainy day. So in the exam, I may ask you a question that's related to some of the things we've covered in the context of that project. But you'll see, I'm not going to be assessing anything having to do with StormCAD quite yet. StormCAD will be on the final exam, but not yet on the midterm. One of the main things that we jumped into very early in the semester was the rational method, because that is how we're going to be quantifying flow rate off of certain areas in the HSB project. So the rational method is talked about a little bit in chapter 9.6, but really it's the notes that had the most detail so far on the rational method. You did some homework problems, and we had a few examples in class that were related to design and sizing of ponds. And you'll remember that after I handed back that pond homework, I criticized some of your designs a little bit for the ponds being too deep. There were some ponds that were like 25 meters deep. And that's not going to be very useful to a town unless it's a very steep town. Remember, the concern that I had was that, let's say you've got a town with just, a moderate slopes. And then here's the river. All of the water from the town gets into the river. If you have a pond that is 25 meters deep, here's our stormwater pond, you're going to have to pump water to get it in the pond. And ponds are supposed to be gravity flow. So, okay, let's say that instead of making it a tower that the stormwater is getting into, so let's make it a 25 meter deep pond. Same problem. You're going to have to pump it to get it into the river. And so a pond can only be as deep as you're able to drain it from. So how deep could we make the pond here? Well, we could make it, if the water level's here in the river, then we could make the pond maybe this deep, because we could still put in a pipe connecting the pond and the river. And if this is the water elevation, as long as it's above the ultimate outlet, then the water is going to drain by gravity. And the bottom of the pond should be able to be drained if it's just going to be gravity flow out of the pond. So when we did stormwater detention design, the calculations are one thing. We're using the orifice equation to calculate the flow out. We've got the flow in, and it's like an hour by hour kind of a spreadsheet that's very easy to set up. And in fact, I hope that you've saved those spreadsheets, because it would be good to go through and remind yourself what the column titles are. If you get a problem like this on the exam, I won't let you use an existing spreadsheet that you've got. You're going to be needing to start with just a blank workbook. And so you either remember what the titles are supposed to be, or you could make a note on your one page of handout that you're allotted what the columns ought to be when solving a pond problem. And you can sort of just derive it yourself as long as you know the concepts. In equals out. Accumulation is in minus out, and so you're finding the pond volume at any time by looking at what came in during a time increment, what went out, and you can sort of prove to yourself what it needs to be. Culverts and HY8, and I'll have the tablet computers available. You can bring your own personal computer if you like, but I might ask you a question having to do with HY8, and so that could be a design or an analysis problem utilizing HY8. And so it was after those initial things that we sort of delved into the book, Chapter 2 with the basic hydrologic concepts, and there wasn't a lot of problem solving there in the basic hydrologic concepts. That was mostly conceptual type questions, and so with climate, where I may be asking you to explain things like maybe the adiabatic lapse rate and what causes rainfall. Remember rainfall, where is that? Precipitation, Chapter 4. Remember the different forces that cause precipitation, and it's essentially lifting that's accounting for precipitation. You know, anytime you make the air move upward, then it's going to decrease the temperature and increase the relative humidity. And there were 3 different forces that cause lifting typically. So any questions about the list of topics, or maybe any conceptual things that have never quite made sense to you that you want to talk about? We've got maybe 5 minutes that we could discuss if you'd like. If there aren't any specific questions, then we'll just finish for now. I do have office hours this afternoon, and I'd be more than happy to have you stop by if anything pops up on the homework or in your preparations for the exam. Other than that, I'll see you for the test Thursday, 9:30. Have a good day.